Right, great. So thank you very much, Pasquale. So I just, for people here, I'd just like to welcome Pasquale Malacaria, who is a professor of computer science at Queen Mary University in London. And he is actually in London at the moment. So thank you very much for being with us here. So Pasquale is famous for his research on foundations of security, information theory, game theory, and cybersecurity. And today he is going to talk to us about quantitative information flow, the theory and the theory of quantum leakage. So thank you very much, Pasquale.
Okay, thanks. Thank you for the invitation. Should I share my screen, I imagine, right?
Yes, please.
Yeah. Where is it? Okay, can you see the screen?
Yes, we can.
Can you see it?
Yes, thank you.
Okay. Okay, so I will talk about two contributions from quantitative information flow to other discipline, information theory and quantum leakage. These works are joined with Arthur Americo and Arman Khouzani. So I'm going to give a rather high-level presentation. So hopefully I'll manage to communicate the ideas. The first contribution is an axiomatic presentation for information theory for general entropy functions. And the interesting point of this axiomatization is really to be able to simplify and prove several fundamental results of information theory within this framework. And the second contribution is quantum quantitative information flow, which is a leakage framework for quantum computation, which is based on the G-leakage framework. So just, typical preliminaries. The object investigation mainly will be information theoretical channels. So these are discrete conditional probabilities, so Py given X, or also stochastic matrices, so matrices of reals between 0 and 1, whose row sum to 1. They model some sense processes. So the row are the input, the columns are the observations. So this matrix model a process with 3 inputs, which are the secrets, and has 2 observations. For example, the second input, the process may end up with observation 1 with probability 0.6 or observation 2 with probability 0.4. In quantitative information flow, what we are interested in is how much an attacker can learn about the secret, so the input in this kind of channels, from the observations. So how do we measure this? So one could take a measure of information. So typically information is measured by some entropy, or a different approach that has come out in the last years is to take a notion of reward if the attacker gets the secret. So this is the framework with gain functions. And as they are relevant for the rest, so just one slide overview of the G-leakage framework. So we have a gain function, and that measure the gain of the attacker when the attacker decides W and the secret is X. And the crucial formula is the posterior G vulnerability. which is the optimal attacker expected gain given a channel PY given X. So here we see we got the maximum, max W. So this is the optimal gain, but in expectation, we have this expectation there, and then that's the channel component PY given X. So why this is interesting? Because depending on what function G one take, there is a wide variety of measures that come out. In particular, I mean, the basic one is a Bayesian one, so where we take as GWX1 if X and Y are the same and zero otherwise. And in that case, so the posterior G vulnerability ends up basically by taking the highest probability given the observation. So this is related to a Rayleigh conditional mean entropy, and is one of the basic measures using G leakage. So what this is framework is interesting at CSF 2016. So Mario Alvin, Kostas Chatsikokolakis, Annabelle McIver, Carol Morgan, and Katusha Baramidesi, and late Jeffrey Smith. So they presented this paper, CSF 16, was a beautiful paper, Axioms for Information Leakage. And this paper gave two contributions. The first is to provide an axiomatization for quantitative information flow that is based over this concept of G leakage, G vulnerability. Well, I thought the work was beautiful, very elegant. One thing that comment to be made, however, is that these axioms for QIF did not recover most known entropy measures. For example, most entropy, Rayleigh entropies, they are not within this framework. So as in axiomatics, they were failing to provide axioms for information theory. So, well, it wasn't the objective there. The objective was really to provide an axiomatic for quantitative information flow. But this is an overview of the axioms. So I'm not going to details, but just we will revisit a variation later on. So we have convex functions. We have posterior as an average. And so, for example, from having a measure as convex function and posterior as an average, one can prove DPI, which is the data processing inequality, is inequality also fundamental in information theory. So, well, we revisited this kind of axioms a bit later on. One comment is that in the same conference, Arman Khouzani and myself, we had a paper called Relative Perfect Secrecy, Universally Optimal Strategies and Channel Design. And again, so from a very different angle, we proposed a general notion of leakage, studied properties. Our angle was to study universal optimality. So we were thinking about strategies in some sort of games that were optimal in the sense of leaking as little information as possible under some constraints, no matter how leakage is measured. So this no matter how leakage is measured is why we use this term universal. And optimal is because it's the minimum leakage. And to formalize this idea of no matter how leakage is measured, we introduced a core-concavity. Now, both the axiomatic work in that conference and our work proved totally independently a general theorem about the data processing inequality, so that processing data can only destroy information. So in the axioms that was proved for the G leakage framework, the G vulnerability, and in our case, we were proving it for core-concave functions. All core-concave functions satisfy the data processing inequality. So our angle, I say, was very different. Why did we came there? I say, really, it was about studying sort of families of guessing games. So the first time I had a research meeting with Arman, we were talking about kind of typical guessing games, and we talked about the Monty Hall problem. And very quickly, I mean, we realized that this kind of sort of paradox in probability theory is really a typical quiff problem. So why should the player change his the door? Is really just because when the game host open one of the doors, he's leaking some information. And in fact, I mean, it's quite easy to define some simple variation of the Monty Hall problem where there is no leakage. And in that case, there is no point in for the player to change his mind. So we found this very well-known problem, is a quiff problem, has this interesting property that you really change your mind because there is leakage. But then, of course, as is a quiff problem, the leakage depends how you measure. So if you measure with mean entropy, you get a different measure than with Shannon entropy. So we started thinking, yeah, in this kind of guessing games, so can we have strategies that are optimal from the game host point of view, no matter how this optimal is measured, so no matter how you measure a leakage of information. And so we worked on this for several months, but at the end, yeah, we reached the conclusion that, yeah, we could find this guessing games where these were happening. Was a very interesting class of games. So we had, and then we had these strategies that were optimal for all possible measures. And so we started looking at how general are, how universal are these strategies. So we looked in the proof of the optimality, what were the minimal condition for which this proof would work. And the minimum condition were the condition defined core-concave functions. So this is how core-concave functions came about. So it was a class of function for which one could define these universally optimal strategies. And core-concavity so includes the G vulnerabilities, but there is much more. In particular, all entropies in the information theory literature are core-concave. So now, how to justify in terms of entropies core-concavity? Because, well, entropy is one thing as a measure of uncertainty. And, well, for example, sometimes if you take a concave function, you can argue that the inequality of concavity is inequality in terms of uncertainty. So what is a core-concave function? Is a pair of functions, eta and f, where f is a concave function and eta is a strictly increasing function. So you just have this pair, and as long as f is a concave function and eta is strictly increasing, that's a core-concave. Now, if you think of a concave function, so a concave function is redefined by this inequality, so it's a function f such that f on a convex combination of random variables is greater or equal than a convex combination of f in the component random variables. Well, you can see that this inequality, well, it still holds clearly, trivially, if we apply to both sides a strictly increasing function. And so that, if you wish, is how this thinking of a measure of uncertainty is still preserved by core-concave functions. And in fact, I mean, as I said, well, Shannon entropy is clearly core-concave because it's just concave. So as eta, you take the identity. But any other entropy is core-concave, but just playing on the eta and the f. In fact, I mean, so all are Radis entropies, all Sally's entropy, and the more general family of entropies in information theory is the Sharma-Mittal entropy, for which all Radis entropies are and Sally's entropies are particular cases, and the Sharma-Mittal entropy also can be shown to be core-concave. So I have this form of an eta and an f. And so we can kind of define a sort of order of concavity, if you wish. So we have concave functions, and all concave functions are sure concave. So sure concave is a beautiful definition. Basically, so this pi less or equal than pi prime is called the order of majorization among probability distribution. So that's order is that pi is more uniform than pi prime. This that's the order of majorization. And so sure concavity as a condition is that if you have a distribution more uniform than another, then f on the more uniform has a higher value than f on the less uniform. So concave are sure concave are core concave, and core concave are quasi concave. So the top in this order of concavity are quasi concave functions. So in fact, I mean, so the core concave is here eta of f of x. So this is the unconditional form, and is not the crucial element in our theory. The crucial element is the posterior. And so the posterior is slightly more involved, but this is really what makes the power of our theory. So given a core-concave function eta f, the posterior form is given this way. So you have the typical average, so where you apply f to each distribution component, and then you take the expectation. So this is the typical average posterior of an entropy measure of that. But then you apply eta outside. Okay, so we call this the eta average. And clearly the unconditional case is just a particular case of this, where you have here just take one element y. So there this falls down to the unconditional case h of x. And clearly there is a simple injection from G vulnerabilities to core concave entropies. So G vulnerability is through a convex function v of g, and so the mapping is the identity for eta, and then minus v of g. So minus of a convex function is concave. The identity is a strictly increasing function. So that's is a very simple embedding from G vulnerabilities to core concavity. But so, okay, so this is the crucial definition for what you will follow. So our axioms, so based on core concavity, then are the following. So here you can see is pretty similar to the one from my estimated colleagues. So instead of having a convex function, we have core concave. And instead of having the average as posterior, we had eta average. But then, so we have a concave and eta average. So again, they imply data processing. And CRE, this is the classical, again, it's a fundamental inequality in information theory that conditioning reduces entropy. So these are the axioms. So to clarify what we have a universe of real valued functions written as eta composed with f for some strictly increasing eta. And we can do this for any real value function just because we can take eta as the identity. And so any real value function can be written in this form. And then, the axioms say H is a core concave. So in that case, F is a concave and eta is strictly increasing. Eta average is that we can write the posterior of H over X given Y in the eta average form, so with eta outside and then the expectation of F inside. And then this CRE and DPI, these are fundamental property from information theory. So condition reduces entropy is that for all random variable X, Y, here, I mean, of course, discrete random variables, H of X given Y is less or equal than H of X. And with equality, if and only if X and Y are independent. And the data processing inequality is that if X and Y and Z are three random variables in a Markov chain, then H of X given Y is less or equal than H of X given Z. So as you go further on, you keep processing, the uncertainty increases. Okay, so these are the statement for each node in these axioms. And well, as you can see, is easy. A very simple consequence of the axioms now is, for example, this statement. So that under the assumption that the function as a posterior satisfy the eta average, so that the posterior is eta of that expectation, then data processing inequality, conditioning reduces entropy, and the core concavity are equivalent. Okay, and so if you want to know, if you have a one entropy and you want to know a candidate entropy, you want to know if satisfy a data processing inequality or condition reduces entropy, you just check that it is core concave and the posterior is an eta average. Now, I mean, this is simple for proving from the axioms, but actually in the information theory literature, I saw some papers, quite good papers, where the authors were presenting some entropy definitions. And then a good part of the paper were technical proof to demonstrate that that definition, that notion was satisfying data processing inequality or condition reduces entropy. Whereas, I mean, clearly they were core concave entropies. So just by the axioms, that properties come for free. So that was quite pleasing to see that. But actually then there are several more things that, so as I say, the thing, the crucial thing from the axioms is that core concavity kind of sort of characterize under this assumption that the posterior is eta average, which is a very general condition, basically core concavity characterized class of entropies that satisfy data processing, and the condition reduces entropy. That's sort of the beginning. In fact, I mean, then there are several other things that can be proved just for core concave entropies. And so all these are fundamental information theoretical properties that we are able to prove, I think, quite elegantly and simply in this axiomatic theory. So here, H is a core concave symmetric entropy. And so the first is this property that whenever you add information, entropy increases. So if you have X and then you take X and Y, so the joint variable X and Y, then the entropy increases. So H of X is less or equal than H of X and Y. And more generally, H of X given Z is less or equal than H of X Y given Z. The second is that Shannon theorem of perfect secrecy generalized to all symmetric core concave entropies. So in any crypto system with perfect secrecy, you always have the entropy of the message is less or equal to the entropy of the key. So that's, again, is a very nice, cute little proof. But I think, I mean, the one that I liked the most is the generalization for Fano inequalities, because Fano inequalities is a fundamental properties in inequality in information theory, which connect a conditional probability with the probability of error. So is fundamental encoding theory and so on. And so what we can prove for all core concave symmetric entropies is the following inequality, that the conditional entropy of X given Y is less or equal to the entropy in this term, where E hat basically is the average error. So for each component in the conditional probability, there is an error. Here is the expected error, so the average error over all components. And if you replace H, so this holds for all symmetric or concave. So if you take as a specific H Shannon entropy, then this inequality becomes exactly Fano inequality. So the Fano inequality from information theory. And again, I mean, what is beautiful is that if you take Fano original proof in Cover and Thomas, which is a very nice proof, but it's still quite, well, one page. But our proof in this system is like 3-4 lines. And so all this is in this paper with Arthur and Arman that we published in Transaction in Information Theory, so conditional entropy and data processing in axiomatic approach based on core concavity. Okay, so hold on, you may say. There were another set of axioms in that beautiful work on axioms for Quiff, which was the axiom for quasi-convexity. And there, so instead of having a convexity, you have a quasi-convex, and then instead of having average, you had the max as posterior. Well, it turns out that, well, in core concavity, the two axioms kind of merge, because the max posterior is a limit case of a sequence of core concave eta average of eta averages. So if you take here this, okay, so you should put a minus here. It should be a mean because we have a concave instead of convexity. But this side here, this is strictly increasing, and there is convex if you put the minus. So you recover the max posterior as a limit construction of eta averages. And in fact, this is not so surprising, because one can prove that quasi-concavity is a limit of core concavity. So any quasi-concave function is a limit of a sequence of core concave functions. And in fact, then most properties satisfied by core concave functions holds for the limit constructions. In fact, I mean, I'm not going to details here, but this is the topic of a paper with Arthur Americo. We had CSF 2021, concavity, core concavity, quasi-concavity, a generalizing framework for entropy measures. So, for example, yeah, you have this limit construction and the Fano inequality, and the other two properties kind of holds for the limit constructions, holding for the whole sequence, also hold for the limit construction. Okay, so another thing, this is for quantum, for quiff purposes. Another interesting result is that the coriaceous theorem also holds for core concave functions. So that's the Blackwell-Sherman-Stein theorem. And in our case, we proved by using some, there is this beautiful paper by Dahl. Dahl is a Norwegian mathematician. It's a paper, I think, matrix majorization, really algebraic, beautiful, and they prove in these algebraic terms the Blackwell-Sherman-Stein theorem. And we just use some of these tools. I mean, the bottom line also, there is the separating hyperplane in all proof for these theorems. But here the presentation in Dahl is very elegant and algebraic. Well, anyhow, as usual, we have that given channel C and D, and such that D is the refinement of C. So you have some other channel R such that D is equal to CR. That's all if and only if for all distribution P over X, H of X given Y less or equal than H of X given Z for all core concave functions H. So that's the standard coriaceous result. And actually, this is a good point to stop these axioms, because in fact, the coriaceous also holds for the quantum presentation. So in fact, I mean, the framework where we define quantum quiff is where it has been proved the quantum equivalent of this theorem. Is there any question so far?
Hi, I just typed one in as you spoke. This is amazing. First, I just want to say that's not a question, but this coriaceous theorem that that links the testing, so to speak, with the manipulation of the C to make a D by post-multiplying by R. Since that holds for concave or convex, whichever you like, functions as well, it suggests that you get no extra testing power from using core convex functions. That they don't, it doesn't make any difference, and that's puzzling.
Well, I mean, if you wish, yeah, I think that's a good observation. But yeah, because remember, you have the difference is that in this the core concave, you have this. The crucial thing is to have this heat outside.
Yeah.
So the heat, whatever is an order, the heat outside will preserve that order.
Of course. Yeah. Yeah. I see. Thank you.
Okay. Okay, so and now we come to the quantum thing, and I'm not a quantum advocate, so I'm just I'm a bit skeptic about all the quantum fever, but what we were doing is just really we read the big quantum textbook. And we were looking for things, how to apply QUIF to the quantum settings. And then we fall down on this paper by Buscemi, Francesco Buscemi. So this Francesco Buscemi is a very interesting person because we already knew some of his work. He's a quantum information mathematician, really. But for example, he proved also independently the Dallenius leakage from Jeffrey work in 2016. So Francesco Buscemi had a different proof, but it was the same kind of result. And he's worked, yeah, on a statistical experiment, a decision-making statistical experiment, and he did this work on a quantum version of that. And we thought that we could basically trick his work and apply for the purposes of QUIF. And this is what really is. So this work is based on G vulnerability and Buscemi's work on quantum statistical decision theory. And again, so I'm going straight to the point, and I'm just show you, hopefully it is very clear how this works. So let's remember that in the posterior G vulnerability, we have this expression. So this is the channel. So this is the model of the process. And clearly, when we move to the quantum world, this has to change, because this is the model of the computation, but this computation is classical, it's not quantum. So what is the framework that we're going to consider? We consider a classical secret, this could be encryption keys, password, etc., and a quantum and the quantum system. So the system starts with the secret X and evolve quantumly, reaching a quantum state, rho of X, and the attacker can observe this quantum state. So now, this is okay. It's not the fact that we start with a quantum, with a classical secret is okay, because all computation that we talk today in security with quantum have this pattern. If you take a shared algorithm for integer factorization, the secret is an integer, right? And the algorithm take that integer and then quantumly will decompose in its prime. A quick key exchange, again, the secret are keys, which are sequence of bits. So that is the typical framework for quantum computation. And now, so what is that really change? Is what we mean by observing. So the observation now, the attacker observed the quantum state. It means that the attacker makes a measurement on a quantum state. This is the crucial difference. So, so here I present you the quantum posterior G vulnerability, and really, yeah, look at this formula. One comparing it to the classical thing. And as you can see, it's pretty much identical. So what do we have? We have a max E at the beginning, and then the last term is different. So let's see bit by bit what that means. So this here, P element here is basically are the measurement apparatus. So you have in a quantum measurement, you may have different possible measurement apparatus, and you choose the one that give the best reward, basically. So you maximize on the measurement apparatus that you can choose. That's there. And clearly you don't have this in the classical case. And then everything stays the same up to the very last term. So as I said, now instead of having this conditional probability that is an entry on the channel matrix, you have something different, which is this trace of rho x EY. So rho x is the quantum state where the system has evolved to. And EY basically is your measurement, with a label Y over this state. And the trace of this quantity is the probability of the quantum state rho x collapsing on the observable EY. So basically you can see is kind of the quantum correspondent of taking this channel entry. Here is the probability of observing Y given X, and here is the probability of the quantum state rho X collapsing on the observable EY. Okay? In fact, so we can show that this classical case is an instance of this more general case. So we can define a set of POVMs and a set and a quantum state. So quantum states, one for each X, such that we recover any posterior over any information theoretical channel. And the construction is simple. So basically you take as measurement a singleton, which is an orthonormal basis labeled by your observations. And then as a state, you take this state there. So these are for the element of the basis. And then here you basically insert the probabilities for the specific channel that you look at. So this, what this kind of motivate that we have a notion of G vulnerability that generalize the classical one and is meaningful in the quantum setting. Is meant to do what we want to do. And not only that, but as I said, the fact that, well, Buscemi used a similar construction and proved that a coriaceous theorem for this sort of vulnerabilities. It kind of make it even more appealing. So the Buscemi approach, so he's I think you know, this is based on this idea of statistical experiments, So you have a statistical experiment is basically an information theoretical channel. There is a state of nature, that's the input, and then there is an observation that come from that state, and and basically you want then to make a decision based on the observation. This is the kind of the basis of statistical decision theory. And classically, so the problem that they were approaching is when it is that different experiment, one experiment is more informative than the other. So when is that an experiment is always preferable to another one in terms of information. And this is pretty much the same a problem in QUIF, where we replace experiment with a channel or a system. So there are some minor difference with Buscemi, but as mainly cosmetics. For example, here it takes this delta instead of the action itself, maximize over a function. What else? Yeah, so the his formulation, this is in the quantum settings, so he looks for the maximum expected payoff. Again, so we have here, this is the collapse of, this is the probability of the state, quantum state rho x to end up with the observation W. And this is pretty much the same as the posterior quantum G vulnerability by doing some reworking. Again, here it takes a uniform prior, if you wish, but that can be readdressed by adapting the gain function.
Could I ask a question here, Pasquale?
Mm-hmm.
Yeah, I'm looking at the formula at the top of this page, which I think was also on the page before. If you look, say at its right-hand side from the sigma W onwards, then it looks like, and you look only there for the moment, it looks like the G and the delta could be merged because both of them contain a parameter W, and you could just take the sum right now and make a new function, you know, Q or something, which was the sum over W of GWX and delta YW. And so the Q would be a function of Y and X. So I was just trying this experiment, so to speak, to think, you know, why can't that be simplified? And then I noticed, of course, that you have at the very left-hand side, a maximum over delta. So that's why you can't do what you suggested. But what it looks like is, if you were trying to see it in a different light, basically the extra expressivity this has over the conventional gain function thing is that you are also somehow maximizing over a class of gain functions. And which class it is the ones that you can make by putting a G and a delta together somehow.
I don't think there is really more power than in the G vulnerability. Is it? So
if you took, say, for example, again, looking at it, you take the P Y given X and distribute it to the left of the sigma W because it doesn't contain a W, so you can pull it out. And then what you've got on the right-hand side is sigma W, GWX, delta YW. I hope I'm saying all that right. And that is a function itself, but it's a function only of x and y. So you might as well write it as some function of x and y. Just, you know.
Well, I mean, you can, I mean, you replace the maximization over delta with the maximization over w, and replace yeah, take this out.
Mm-hmm. I don't know, maybe that's a kind of complicated question to ask in the middle of a talk, but I was just wondering, actually, you know, what was the structure of this?
So he has different models, and I think this is relevant for other models that he considered, but for this model where the secret is classical, it boils down to pretty much the posterior G vulnerability. I don't think it makes a difference there. But his framework is more general than this, so that's the reason. But I can look a little bit in details later on. So, yeah, okay, so this is basically, again, in the quantum formulation is going to be translated exactly in the same way it was translated in the quantum G vulnerability. So the whole term there is going to be the probability of state rho x collapsing EW. So this is at Buscemi's theorem. So these are the quantum system as we were talking about. So our system where X is a classical, is just a set of items with some probability. And then we have a quantum system that evolves to some quantum states. And then the result says that there is a statistical morphism from this system to this system. So that maps rho x to sigma x, if and only if for all gain functions G, this expected payoff over R is greater or equal than the expected payoff over S. So if you remember this quantity here. So basically, if the posteriors are in this order. So now, basically what we there, this would be the channel refinement, because sigma x, rho x are kind of the channel, and this statistical morphism is a sort of the refinement. So it's a bit, it's not as kind of syntactic, if you wish, like in the classical case, where here we really have a matrix, a product of matrices. There are some additional conditions. The statistical morphism is quite a technical definition, but as a statement is pretty much what you would expect, lifting the coriaceous to the quantum settings. Okay, so that's a little bit what I wanted to say. So the first, I wanted to present this general axiomatics for information theory based on core-concavity. And the second is about the extension of QIF to the quantum settings, defining quantum G vulnerability. And in both cases, for both frameworks, there is a coriaceous theorem that holds. And that's it. Thanks.
Well, thank you very much for that. Does anybody have any questions for Pasquale?